So it is due to Noether. She is a lady mathematician. Mathematician as well as physicist. So last time what we have done. Okay. So let me recapitulate what we have done in the last lecture. We have tried to construct a Lagrangian from symmetry arguments for a free particle. Okay. And then we have said there exists. Okay, so there is a kind of theorem, or there is a theorem that gives us the explicit relation between the conservation laws and a continuous symmetry. Okay, if a system possesses a continuous symmetry, it means there exists a conservation law. A continuous symmetry possesses a conservation law, or if you are having a conservation law, that means it has come from a continuous symmetry. That means the system has a continuous symmetry. Clear? So this kind of relation between the two is the content of the Noether theorem. Okay. So in other words, so our statement for the Noether theorem is: so if you are having continuous symmetry, okay. So it's like this thing. So you are having a conservation. So we are doing it in the classical system, is it? So since we are doing what we have done till now, that's all the classical physics we have done. Okay, there is nothing quantum. So later on we will see. Okay, and in the next semester we will look for the quantum version of this Noether theorem. Okay, we will look for how we can generalize this kind of concept to the quantum field theory. Okay. For the time being, we are in the classical domain. Okay. So now let's start. Okay, let's try to prove this kind of statement. Okay, let's have a proof for this thing. What I will do, okay, so let's assume we are having a field of phi of x. Okay, so this phi can be a single field, it can be many fields. Okay, we can put an index on this phi, let's say phi a. Okay, so it means it is having a components. Clear? Got it? But I will not use the number of components. Later on I will simply I will do it just for the simple, one field kind of thing. I will just take one field at a time. Okay. So let's make a variable. Okay, how we define the action first? So this is our action. So we will in the 4-dimensional space time. Okay. Okay, so now, okay, if the system possesses a continuous symmetry, clear? So what will happen if I make a change in action? Okay, so if the system possesses symmetry, let's say phi satisfies the equations of motion, clear? Okay, equations of motions are satisfied for this field of phi, and I am saying there is a symmetry existing in a given system, then the variation of this action is equal to 0. Okay, you got my point. So the first thing we have done last time, what we have done, we have varied action using an action principle from where we got equations of motion. Now what I am saying, equations of motion are valid, clear, and additionally there is a symmetry, clear. Because of the symmetry, variation in S is equal to 0. That's not the action principle, clear. Action principle helps you to figure out the trajectory or the equations of motion of the particle. Clear? Here, what we are imposing the condition that the variation of this S is equal to 0 because of symmetry. Clear? Got my point? And we are assuming this phi satisfies the equation of motion. Okay, what I mean by that, okay, we say phi satisfies equations of motion like this thing. So Euler-Lagrange equation. Okay, and if let's say L is invariant under some continuous symmetry, that means it possesses symmetry, then delta S is equal to 0. So these two conditions will be used in the proof. Clear? So now let's start. Okay. So I will use these two conditions. So let's vary the position coordinate. Okay, let's make chain. Okay, this x mu like this. It is an infinitesimal change. X mu goes as some x prime mu is equal to some x mu and delta x mu. So this is an infinitesimal change. Clear? So let me start from a basic point. I am simply changing the coordinate. Okay, by an infinitesimal amount. What will happen to the field? Field will change. As a result of this kind of transformation, the fields will change. Okay. So what is the change in field? Let me write this phi of x. So it goes to some, because now x is also changing, so I'll put in x prime. So that's equal to some phi of x plus some variation on phi of x. This is all because of I'm changing the coordinate. Okay, clear? So in other words, you can change both the two things simultaneously. You can change this x as well as the field, clear? By an infinitesimal amount. What will happen to the action? Action will change, is it? So let's say delta s represents me the variation action. Okay, by the way, this action is defined over some volume omega. Let's write our volume is what? Omega. So I'll write now the change in this action. Okay. So how I define the change in action? The action defined for the new field, this phi prime x prime field, minus action defined for this phi of x. Is that the change? Just the difference between the two actions. Okay. So what I mean by that, so it is something like this. L of phi prime x prime partial mu prime. Okay. Phi prime x prime. So this is the action defined where? At some volume omega prime. Clear? Because I have changed my coordinate, so the volume will change. Clear? So let's represent the new volume to be what? Omega prime minus the action defined at the previous volume. Okay? Phi of x partial mu this phi of x. Okay? Clear? So okay, so now let's look at the first integral here. So you are having integral, forget about this omega prime. This is an integration over which coordinate? X prime, clear? And this is integration over x. Now look at here. So you are having x prime here, x prime is here, is it? This partial mu, it is actually d by dx prime, clear? Or partial by partial x prime, clear? And you are having x prime here. So what the coordinate it is? So what is x? It's a dummy variable, clear? Because there is a sum or there is an integration over that coordinate, clear? So and here you can see this x prime is actually a dummy variable. You can replace this dummy variable by any other kind of variable, clear? So I will drop this prime here on x, clear? Okay, so in this case, so you are having x prime is a dummy variable. Okay, so we replace x prime by x in. Clear? Got it? So, any question? Now, so as that step, I will remove this thing. Okay. Clear? Okay, so this is our next step. Just I have removed the prime is on x, not on phi. Phi is a different thing. Eh? Okay, phi is changed. Clear? Okay, so now what I will do, okay, so I will write this action. So since this is the difference on actions, okay, so why from this omega prime has come? By changing the coordinate, clear? So it has come actually from this omega. In this volume I have changed my coordinate, I have got a new volume, clear? So let's say you are having, this is our surface kind of thing. Okay, this is our initial volume. Okay, now your volume has changed to some this thing, this omega prime. Omega prime contains omega itself. Got it? So what I will do, I will write this thing as an integration of omega plus a term which will represent this amount. Clear? So much on? You got my point. So I will do it this way. Okay, so I will write this action delta S as omega d4 of x L of phi of x phi prime of x partial mu phi prime of x minus integral omega d4 of x L. So I am doing it from the simple perspective. So there is another way, so that I will show you later on. So now look here, I have so what I have to add? I have to add an action for this very part. Clear? So because this is a linear, so this is a linear operation, this integration. So you can put an integration over a given interval as a sum over smaller steps. Clear? So that means it will be an integration over this omega and this. Let's call this amount as how much? So if this is an infinitesimal, let's write it as partial omega. Clear? So much or a small amount. So I will put it as like this thing, partial omega. So it is d4 of x L of phi prime. Here the field is prime. Got it? So let's call this as equation first. Everybody? Any problem? So let's rewrite this very term first. So let's rewrite it. So you are having this partial omega. So now let's figure out how large is this omega, what this partial omega represents. Let's look at this very term carefully. So if my initial value, let's say I can write this omega prime. So since this omega prime and omega has this much of difference, partial omega, clear? It's a very small infinitesimal change, clear? Infinitesimal change in the value. So that means I can expand this omega prime in terms of omega. Can I expand? Yes. Because what I am doing, forget about this omega. So why now the phi prime is actually in the volume omega prime. Although it also contains this omega, but it is in this region, omega prime. So it is not same as this omega. Got it? So omega prime and omega has a difference of this partial omega. Clear? So phi prime is defined in the omega prime. Phi prime has come from actually the change in the field. You got my point? So much now? So now let's expand this value, omega prime, in Taylor series expansion. What I can do, I can write this as omega plus some partial omega. Clear? Can I write it?
Yes, sir.
Plus higher order terms. So I can expand it like this. Since this is an infinitesimal amount, so what this will represent, this partial omega?
Small difference.
It's a small difference, exactly. Tell me. So I can write this omega prime minus omega as of the order of what? Partial omega. Since it's a differential, is it? Understand here, it's a differential, or it is a differentiation of the volume omega. What that will represent to me? What is the derivative of a volume? That is surface. Clear? So that means this much of difference, or let's say this annular region, small region, this infinitesimal region, will represent up to the first order as a surface. Clear? Samushaman? It will not represent the volume, but it will represent it. It will represent the surface. Clear? So we have shown it. So that means this is simply the surface element. Infinitesimal surface. I will write surface area. because surface means nothing, surface area. समझ आओ? So let's give an example. Let's say you are having a volume of a sphere 4 by 3 pi r cube. What is this dV by dr? Tell me. What is dV by dr? It is 4 pi r square. What is that? Total surface area of the sphere. So that means the derivative represents with the surface area. Clear? So now you got this is a surface. Okay, so what it means? So in other words, this is an integral over a surface. It's not an integral over volume. Clear? Okay, so now let's look at this object. So you are having this d4 of x. d4 of x is a volume, 4 volume. So let's say if I have to write volume, it is actually the product of the lengths, essentially, is it? If I have to write, let's say, volume of a cube, what you will write? Length cube. So that means you multiply simply lengths. Now if I have to, if I know the surface area, so you multiply surface area by the length, is it? So here I am having 4 volume. Huh? So let me assume your volume is, okay, your surface area is what? ds. Clear? So what I need to multiply it? Length. Clear? If your surface area is S, ds is the small surface area of the 3-dimensional, let's say, space, okay, and you multiply another length. Clear? So what it will yield me? Volume. So that means I can, okay, so this is simply the symbolic representation. It is not necessarily true, but it is simply what? From the dimensional analysis, I am saying this object is having a surface area and this is the length. Clear? So that means it will give me the 4 volume. Clear? I need to figure out what order of magnitude of this very term. I want to extend, okay, retain only the up to the order of certain terms. Clear? So, okay, so you will see in a moment. Okay. So let's write this L. So L is a function of phi prime, partial mu phi prime. Okay, so it is a x. Okay. So let's extend this by Taylor series extension about phi. Clear? So make a Taylor series expansion around phi. So what you will write? You will simply put it as L of phi, partial mu phi. Forget about this prime, plus partial L by partial L by partial phi multiplied by delta phi. Clear? Is it true?
Yes.
Okay, so plus other order terms which will be having delta phi square. So okay, so now let's multiply this d4 of x. So what? Okay, so you are having this d4 of x L phi prime partial mu phi prime. Clear? So let's check it. So how much is that? So these are both infinitesimals. Clear? So let's forget about this ds. dx is our length. Clear? So let's take this infinitesimal length. So I will be having now ds dx L. Clear? So this very term plus partial L by partial phi. So ds dx and this delta phi plus j. Okay? Clear? Now look here. What is the order of infinitesimal here? 2. It is order of dx square kind of thing. Clear? So what is the order here? Cube. So you are having 3 infinitesimals are multiplying each other. Clear? So what would be the next term? That will contain 4. So that means it's very small. No? So I can ignore all these higher order terms. Samajh? So I can ignore. Okay, so this I can write simply as like this thing. Okay, so ds dxl plus order of, let's say, dx this delta phi. Clear? Because they are very small. Huh? So since higher order terms, their contribution is very small, so I can ignore those higher order terms. Clear? So in other words, essentially this product is simply equal to, what is this L? So let me write. So it is ds dx L phi of x. Okay, partial mu phi of x. So where that is defined actually? That is defined in the volume omega. Clear? So samajh aaya?
Yes, sir.
Got it? Samajh? So what I okay, so this object I can simply write as now integral over a surface, clear? d4 of x L phi of x partial mu phi of x, not primes. Clear? So that means in this very small region, okay, so in this very small region, I can essentially write this product as this thing, as an integration over the phi fields, okay? So the phi is not here phi prime, it will be, okay, up to the certain order, up to the quadratic orders, so it will be simply equal to phi, clear? Got it? Okay. So let's write this thing. So therefore I can write integration over partial omega d4 of x L phi prime of x partial mu phi prime of x. Okay, so this I can write. Okay, so approximately equal to partial omega d4 of x L phi of x, okay, partial mu phi of x. Okay? So there is another way to do it. Just introduce the Jacobian and show that the Jacobian is of the order of unity here, but I will not do in that way. So it is the simplest of the way to do it for you people. Okay. So now let's rewrite it. Okay. How to write it? Yes.
Gauss.
Yes, a Gauss theorem. Yes. Okay, good. Anybody? So I will apply the Gauss theorem, but how? Okay, so let's write it. So this I will write. So this is actually equal to now d4. Okay, d4 of x I will write something like this thing, dx lambda over partial omega. Clear? Can I write it? ds is the surface and what this is? Line element, and then you are having this L phi of x partial mu phi of x. Clear? So this is the object I will take care of. Now you are having a surface and the vector. It is the dot product of the two. Clear? So apply Gauss theorem. So it will be, okay, so you apply now the Gauss theorem. So it will be integration over volume. Okay. Now it will be simply equal to d4 of x. Now then partial lambda of this vector. It is simply, let's say, v dot s. Clear? Like this thing. If you remember, so you are having partial omega f. Okay, let me write f mu ds mu is equal to integration over omega partial mu, let's say f mu integration over volume. Clear? Is it true? Okay, so now you are having this as a vector, so you put a like this thing dx lambda. Yeah. So L is a function of this phi. Clear? Samajh aa? Got it? So that means I have converted this back into the integration over volume. Got? Okay? And this L now depends only on the fields phi of x and partial with phi of x. That means fields phi of x. Okay? So this is okay. So let's call this equation as simple. Now let's look at this very equation. This the first two terms. First and second terms. Now look at the first and second terms. Any problem till that point? Okay. So let's look at this very term. So you see d4 of x, d4 of x. It means you are having this L minus this L. Clear? What is the difference? So you are having L at point, okay, phi prime, point x, is it? And you are having here L, function of phi of x. So it is something like this thing, this kind of difference. F prime of x minus f of x. Okay, coordinate is, this point is same. Huh? So you are simply changing the function at a given point. So that means we call this this difference as a fixed point difference. My coordinate is same, x, clear? But what is different? Function. Clear? You are having f prime here, you are having f. Okay? So such difference we call as a fixed point differences. Okay? And then you make a, you subtract it from the another function f of x. Clear? So we usually write this as delta. This delta means f prime x prime minus f of x. This delta bar f means a fixed point difference. Clear? So that means in order to evaluate this very term, I need to express this fixed point difference in terms of this difference. Okay? The infinitesimal variation. Okay. Or we sometimes call this as a fixed point variation as well. Fixed point difference or the fixed point variation. Okay, so now let's write it. Okay? Okay, so let's try. So I have this term. So this is the term what we are going to evaluate. Okay, for that matter what I will do, okay, so let's write this delta f for, okay, so variation in f, not fixed point variation, simple variation in f. How I will write it? F prime x prime minus f of x. Can I write it? Any problem? So now this I can write as f prime x prime minus, okay, let's write it as f of x prime plus f of x prime minus f of x. Can I write it? So simply you can cancel. I am just adding the 0. Clear? So what this object is? So this is fixed point variation of f. Clear? Is it? So now here the point is x prime. It doesn't matter. X prime is fixed. Clear? You are having x here, but I have written as x prime. Clear? So there is no problem. Point is fixed. Only the difference makes sense. Okay? So now let's expand this by Taylor series expansion. This f. So this I can write as f of x plus, anybody? Partial mu f of x. Clear then? When you say? There is a multiplication term as well. What is that? Delta x. Okay, plus order of delta x square minus f of x. Clear? Because if you see the x prime is actually x plus the delta x. So that's why you are having delta x here. Clear? So this cancels in this thing. Or in other words, I can write this thing. Therefore, the fixed point difference delta f is simply equal to the variation of f minus partial mu f. Okay? Delta x. Clear? So this is the relation between the two. Okay. So now let's write this thing. Okay? Let's write this thing. Okay. So that we write this as. Okay. So let me write it. Everybody has followed it? So what I will do, I will just make a Taylor series extension of this L of phi prime. Clear? But the point is fixed. Clear? Yes. Someone Shaman? So let's do it. So you are having this d4 of x, then you will write L of phi of x, okay, partial mu phi of x as a Taylor series extension, the 0th order term, then plus partial L, you vary with respect to phi. Clear? Partial L by partial phi. Then I will write what? Fixed of phi. Why? Because you are having here x and x, they are same. You are just changing with respect to the function. Okay, so what you are having? You are making a Taylor series extension about this very function, phi of x. Okay, and the point is same. That's why you multiplied by this delta bar phi. Otherwise, if it would have been, let's say, x prime, then you can simply put as what? Delta phi. The way we have done, deriving the what equation of motion, Euler-Lagrange equation motion for the field. Clear? There we have written actually delta phi. Okay. So then you are having the variation, another variation, partial L by partial mu phi, then this delta bar of partial mu phi. So I think is it visible? Okay, then you are having minus L. Okay, then you are having this minus L of phi partial mu phi. Clear? So this L and this L cancels out. Huh? Question? Any question? Good. Okay, so let's do it. So you are having this as d4 of x. So what you are having? Partial L by partial phi. Okay, so let me write it for you people. Okay, plus partial L by partial mu phi. Then you are having partial mu delta bar phi. Okay, so clear? Okay. So now what I will do? Okay, so this I can change. Now I will use the Euler-Lagrange equation. Clear? So what are the Euler-Lagrange equation? This partial L by partial phi is equal to partial mu partial L by partial mu phi. Clear? So you are having Euler-Lagrange equations. Okay, partial mu partial L by partial mu phi is equal to partial L by partial phi. So that means I will put it in terms of this derivative. Clear? Got it? Okay. So this I will write as d4 of x. Okay. Then I will write it as partial mu. Okay. Now if you look at the two terms, so when I put this here, so you are having the differentiation of this very object, is it? Multiplied by this thing. So you are having here, this term is here now, multiplied by this thing. Then you keep this as such, and then the differentiation of, it is the product rule. Clear? Shall I skip that step? So I will simply write it as, so once you put the value for this thing, here you can write it as like this, partial mu, partial L by partial mu phi, delta bar phi. Clear? And where it is on the volume omega. Okay? So now let's write the total action. I mean this delta S. Okay, so let's call this as equation third. Use third. Use second and third in equation 1. So what we'll get? Okay, so what we'll get? This delta S is equal to d4 of x or volume omega. Then you put as partial mu, partial L by partial mu delta bar phi this way, and then what is the another term? Minus or plus? Plus, huh? So what? How much is that? Partial lambda delta x lambda L r. Okay, let's write only L. Another term, huh? Clear? Okay. So you can take this partial, since you are having partial mu, let's put mu here, huh? Okay, so you can write it as simply as omega d4 of x. So since this is a dummy variable, you can put this lambda as mu. Okay, so you can use as mu here. So then you take partial mu out. What remains there? Partial L by partial mu phi delta bar phi plus delta x mu L. Clear? Got it? Okay. So now let's write this delta bar. Okay, what is delta bar phi? Delta phi. Okay. Okay, so let's write it. So it is integration over volume omega d4 of x partial mu partial L by partial mu phi. Let's write this delta bar. So it will be delta phi minus, so let me write partial lambda phi, okay, then you are having delta x lambda, okay, like this. Why? Because you are having mu is already a dummy variable which we have used. Now this, the mu there, it's a dummy variable. For that I have written what? Lambda. Clear? Or you can put a nu. There is no problem. If you wish, let's put a nu. It doesn't matter. Okay, so let me write nu for you people because you like nu. Okay. So it is delta x mu. Okay. Yeah. Kind of. Okay. So now let's gather the terms together. Okay. So let's put the terms together. So you are having integration over d4 of x over volume omega partial mu. Okay. So you are having partial L by partial mu phi delta phi. Then you are having minus. Okay. So what you are having then? Okay. Anybody? Where is it? Okay, so then you are having minus partial L by partial mu phi. So partial, so okay, so I will write it as partial mu phi delta x nu like this thing plus, okay, so this delta x mu I will write as g mu nu delta x nu L. Can I write it?
Yes.
Okay, so this delta x mu, so nu will get contract, mu will come here. So since, so I just raised it and lowered the index, the dummy variable. Clear? Okay, so you can take out this delta x nu. So I'm simply increasing the number of steps, nothing more than that. Okay, so you are having partial L by partial mu phi delta phi minus, okay, so what is common? Delta x nu. So I will write it as t mu nu delta x nu. Okay, so where t mu nu, that's equal to, okay, partial L by partial mu phi partial nu phi minus g mu nu L. Since I have taken this minus out, that's why you are in minus here. Clear? Got it? And let's define a quantity. Okay. Okay, so let's define another quantity, J mu. Okay, so we are having this J mu is equal to partial L by partial mu phi delta phi minus T mu nu delta x. Okay, so let's define this very quantity. Okay, so T mu nu I have defined already, and I am defining this object, whatever is here, I am defining it as J mu. So therefore I can write this variation in S, so that's equal to integration over omega d4 of x partial mu J mu. Clear? Now if there is a symmetry, okay, a continuous symmetry, the variation in S is equal to 0. Clear? So this object is, okay, so if there is no symmetry, current is not, so we call this as a current, it need not to vanish on the boundary. Clear? And this is true for any arbitrary transformation. This kind of formula where you are having the equations of motion are satisfied, this is true. But if there is now, in addition to the equation of motion, if the, okay, particle satisfies the equation of motion, in addition to that, if you possess symmetry, okay, so then this variation in S is equal to 0. Okay, so if there is a symmetry, continuous symmetry implies this variation in S is equal to 0. So which implies what? Partial mu J mu, that's equal to 0. So it means you are having a conservation law, and J mu is conserved quantity. Clear? So we call this J mu as a Noether current. Okay. So now let's look at what it gives us. Everybody followed it? So it's a 4 vector. This quantity is a 4 vector. Okay, you can be having a tensorial equation. Okay, more than that indices. Let's say mu nu, and so on. So if you are having only this thing, then you are having that kind of quantity conserved. Okay, so those we can see like in angular momentum case. Okay, so you will be having a 3 tensor here. Okay, only one index is contracted, all 2 indices remains as such. Clear? Then we can say that quantity is actually a conserved quantity. Okay, so let's define a quantity. Okay, so let's rewrite it. So I can write it as partial 0 j0 plus partial I ji is equal to 0. Where what I have done, j mu I have defined it as j0 and vector j. Clear? Okay. So what this is equal to? It's simply equal to partial j0 by partial t, okay, is equal to, anybody? Minus del dot j. Clear? So let's integrate our volume. 3 volume, integrate over 3 volume, rather d3 of x. Okay. So a special volume I should say. So let's write special volume. Okay, so what it gives me? So you are having then partial by partial t integral j0 d3 of x, that's equal to minus del dot j d3 of x. So you can use the now. So this is our volume V. So you can use the Gauss divergence theorem. So it will go as surface. Let's write surface S. So it will be simply j dot ds. Clear? So let's define a quantity. Q is defined as j0 d3 of x. We call this as a Noether charge. Okay. So it's known as a Noether charge. Okay. So now, since if there is no, okay, so these currents need not to vanish on the boundary. Okay. So only in the symmetric situation they vanish at the boundary. Clear? Because we are assuming a symmetry here and saying, let's say current vanishes on the boundary. Clear? So in that case, so this will go to 0 at boundary, because S will tend to the infinity. Okay, so these we don't have current, any kind of current on the boundary. What it means? So it gives me, so this is defined as Q. It gives me dq by dt is equal to 0. So which implies Q is conserved. So you are having both neither current and neither charge as the conserved quantities. Clear? Got it? Okay. So let's take an example, simple example. Any question till now? So this is actually the content of the Noether theorem. So let's say we know if the system possesses translational symmetry, what happens? Momentum remains conserved. Okay. So now let's do the translational symmetry, translation invariance under in 4 dimensions. Clear? So sure that incorporates both time translation as well as space translation. Okay, so let's do it. Okay. Okay, so this is useful to me. Okay. Let's take this kind of change. In case space-time translation. Okay. So let's make a translation, a 4-dimensional translation by a fixed amount. Clear? And say you are having this kind of symmetry is there. You know translation symmetry is a continuous symmetry. Clear? So we have done it. Okay. So what I mean by that, so this x mu goes as some x prime mu is equal to x mu plus a mu. So a mu is a 4 vector. It's a constant quantity. So it's a constant. A constant. So you are making a translation by a fixed amount of a. Clear? So since I am just making a coordinate transformation and there is no field at all, there is no variation in fields, clear? I am not changing the fields. What I am doing? I am taking some object by some amount, clear? Got it? And I am not changing any kind of fields. So which implies actually you don't have the variation of the fields. Delta phi is equal to 0. So this defines your space-time translation. You are not doing anything with the fields. You are simply displacing. Let's say the pen, displace it by the same, okay, some amount. Keep the pen, fix it. Okay, the same pen. Clear? Okay. So what it means? So now let's look at that. So when you don't have, the field, okay, so this delta phi variation is 0, clear? Okay, so what it means? So you have only this very term is remaining. So it means that, okay, this J mu, your current is simply, okay, so just tell me what is the amount, this delta x here? Let's say delta x mu. So how much is that? That is simply A mu. So x prime minus x is equal to A mu. Clear? So this is a small change. So I will write simply it as A mu. Clear? So much everyone? So since A nu is a fixed quantity, what is conserved quantity? So okay, so the conservation rule, partial mu J mu is equal to 0 implies, okay, so you are having this thing. So it implies therefore partial mu T mu nu, that's equal to 0. So now look here, you are having a rank 2 tensor and there is only the differentiation with respect to mu, clear? And only one index is contracted. So it means you are having a conservation law, okay, you are having a conservation law and the conserved quantity should be a vector quantity. Okay, so in the previous case, you are having only this thing, partial mu J mu is equal to 0. What was the conserved quantity? Charge. And that is a scalar quantity, that does not possess any kind of index, clear? So now what you are having? So it means we are having, so what is conserved? So that it means you need to integrate over, let's say integrate over volume d3 of x, okay, t, then so keep the index as such, this new, okay, for this index you put a 0. Got it? So that means there is no index, nothing corresponding to that. So let's call this, okay, so this means this object is a conserved quantity. So we have done this in electrodynamics as well. There I have told you in detail how to write these things. So we call this as, okay, so this is our what? Noether charge. So integration of, when I am integrating over the volume, so it means it's a Noether charge, clear? And the Noether current is simply what? T mu nu. Okay, and it's a rank 2 tensor. And you are having only the conservation with respect to this index. Okay? So I will write this as P mu as a 4 momentum vector d3 of x t0 mu. Okay, so we call this as a 4 energy momentum. Okay, energy momentum vector. So what that gives me? Energy as well as momentum. We know if there is a, let's say, space translation invariance is there, so it gives me the conservation of momentum. And if there is a time translation invariance, it gives you the conservation of energy. So now let's check. Since this P mu is a conserved quantity, so it implies therefore let's take this P0. So it gives you the energy. So okay, so how much is that? Equal to integration d3 of x t00. So this t00 represents the energy density. Okay? Clear? So we will do it in detail for different kinds of fields. Okay? For EM field we have already done. I will repeat that exercise here. Okay? So and you are having now PI. So those are simply your momentum vectors. It is, so this gives you the momentum density. Okay? So and PI is the free momentum. Okay? So these are the conserved quantities. Now if I assume, let's say, there is a invariance and rotations, what I should get? I should get angular momentum to be conserved. Clear? So this will be the exercise for you people. Okay, let's assume there is a invariance and a rotations. Clear? Okay, so you change your coordinates. Okay, and assume there is what you are having, invariance and a rotation, and show that you will get a conserved quantity as an angular momentum. The Noether current, what you will get is an angular momentum. Clear? So, or in other words, the Noether charge, I should say the Noether charge, what you will get is the angular momentum of the particle. Clear? So this is an exercise for you people to figure it out. Clear?